Thank you for joining us today. So I'm gonna go through a quick overview. My name is Periel Jedidi. I'm the marketing and communication leader for Spatial. For those who may be less familiar with us, Spatial is a leading provider of 3D software development toolkits for industrial technical application. Our 3D modeling, 3D visualization, meshing, and CAD translation toolkit empower application developers to create market-leading products, stay focused on their core competencies, and accelerate time to market. With over 30 years of expertise, our toolkits have been trusted by some of the world's most recognized software developers, manufacturers, research institutions, and universities to bring their innovation to life. We are very excited to host this Meshing Essential webinar presented by Arthur Bierler, our meshing product lead, who will share valuable insights into how our meshing SDK can enhance your application. It's great to see how many of you are attending today. Before we begin, I just have a few technical notes to share. I will put them in the chat so you can keep them in mind. We are very pleased to have your questions, but we will have a dedicated Q&A session at the end. So please feel free to send in your question in the chat during the presentation, and we will address them at the end. If you have very specific technical questions, you can still raise them. They may not be answered today, but don't worry. Your technical account manager will follow up with you, or a technical account manager based on your profile, obviously. This webinar also is being recorded, and the recording will be available on demand on our website by next week, kind of a Christmas gift. Now, with further ado, I will hand it over to Arthur to begin this session. Arthur, the floor is yours. I think you can wait 1 minute, maybe, but
for sure. Yes, we will do that. I see more and more people coming, so yeah, we'll wait. We will wait another minute. But yeah, thank you, Ferial, for this introduction. Thank you everyone for coming to this webinar. Yeah, a lot of people, so very exciting to see you all there. So yeah, let's just wait a couple of seconds to see whether or not the numbers stabilize, and then we will move forward with the presentation. All right, so I think we can go ahead. So yeah, hello everyone. Thank you for joining us today for this Meshing Essentials webinar. As Feriel introduced me, I'm Arthur, and I will be your host for this webinar. This presentation is of interest mostly if you have an existing application that you would want to take to the next level by introducing some simulation workflow in it. Thus, I know there are a lot of different profiles attending this presentation today. And so I want to emphasize that those who will make the most out of this webinar are non-experts on meshing, or people that know a bit about meshing but would want to get some pointers to quickly get started, get usable results, or people that would want to get some examples of advanced workflows that are possible to implement using our tools. So the focus for this session is just introducing meshing as part of the CAE workflow as we see it at Spatial. And so I apologize in advance for the more technical focused people that are attending today. There won't be any deep dive into technical features during this presentation. So the plan for today is as follows. So first, I will set the context for talk about what's our vision for meshing, what are our typical points and issues that to take into account when dealing with mesh generation. Then I will cover the very basics of surface and volume meshing and what controls we recommend to use to generate simulation-ready meshes in the shortest amount of time. And before the Q&A session, I will give you a couple of examples, interesting examples, in my opinion, of advanced features that you could implement in your application. All right, so let's get started by talking about the typical simulation or analysis workflow. We see it as a 4-step process. So first we have everything that happens within the context of a CAD kernel or a modeler. So that's going to be any interoperability that happens for importing models, creating, modifying the geometry, performing Boolean operations, these sort of things. The second step is the preparation step for the simulation. At this point, there will be the actual mesh generation. And there's also going to be the description of the initial states of the simulation and the boundary conditions. Then the first step is the actual simulation. So the solver will compute the numerical equation across the simulation domain using the initial state as well as the boundary conditions. And the fourth and final step is kind of a results visualization and analysis step where we process the data to validate models, geometries, design decisions, etc. And it can also include content creation for demo purposes or marketing purposes. In this context, this workflow, meshing is the critical link between the geometry and the solver, and thus we have to make sure that the mesh generation process, is well integrated and produces reliable results tailored for the solver. I'm saying tailored because a mesh suitable for CAE application is a very special type of tessellation. There are many types of meshes that exist out there. Some examples are on your screen right now. And they are useful for a wide range of applications, from physically based rendering, graphical applications, to terrain scan, for example, or engineering scans. But they're not suitable for a CAE context because the solvers we deal with in CAE are modeling complex physical phenomenon, and the numerical equation approximations that are implemented in these solvers, they rely on mathematical constraints that have to be respected in order to ensure results accuracy. So I want to give you two quick examples, two well-known examples of situations where you need to respect mathematical constraints. The first one is FEA solver validation. There, we usually want to have a consistent tessellation across an entire geometry in order to properly observe the convergence towards a solution when we're using more and more refined meshes. And the second example is called the CFL condition for finite differences solvers. This condition, it has to be respected to ensure stability of these solvers. And here, for simplicity, the example is for 1D cases, but we already see that the condition depends on delta x, so that would be the equivalent to the mesh size. So the stability of the simulation depends on the input tessellation. And these are handpicked examples, but there are many types of other industry-specific solvers out there to model different types of behaviors. We can take a couple of examples. In the plastic injection industry, for example, there are solvers that model how the plastic flows through a mold, how it cools down, where weaknesses may appear in the geometry, etc. In 3D printing, there are solvers that model how effective is a given printing nozzle, how it draws air from outside and maybe create bubbles in the heated plastic that will later create discrepancies in the printed geometry. Or in a completely unrelated area, the medical field, there are also solvers that exist to model how the heart of a given patient beats with and without artificial parts in it. You have other examples on your screen, but the where I'm going to with that is that all these solvers, they have very different constraints regarding the type of mesh they support in order to get meaningful results. So in order to support this variety of needs, at Spatial, we provide a complete set of automatic meshing components that are able to handle various types of inputs. They are able to generate a wide variety of meshes for different use cases, and they also have a large set of parameters in order to make them tightly fit the needs of the application. However, this high level of customization can be a bit overwhelming when first being introduced with the product. And so in the next part, I want to talk about some of the usual control we recommend to use when dealing with meshing when you are not an expert and you just get started. The first usual question to answer is what type of element is supported by your solver. Typically for surface mesh generation, our products, they are based on incremental Delaunay methods. And so we primarily support fully unstructured triangular meshes, but we also provide capabilities to generate quad dominant and full quad meshes to a more limited extent. Once you have chosen the type of elements that you want to generate, the more important question is how to control the mesh size in the mesh. We have two concepts that usually come into play. We call them physical or absolute sizing and geometric or feature-based sizing. Physical sizing, it's used to generate meshes with a consistent size across the entire geometry, while geometric sizing, it's used to approximate surfaces considering only the local curvatures. So when working with surface meshing, we usually recommend to play around with these two concepts in order to get the results that you're looking for. We have three ways to work to combine these two. First one being to use only a physical sizing where flat surfaces and details are well captured. The second being using only feature-based sizing. Using this method, as you can see on the third image on the bottom of the screen, the mesh is coarser than in the first example with, well, in this location, it's a bit denser because there are curvatures, but across the entire mesh, it's going to be coarser because flat surfaces, they are not well approximated. And so there are some high aspect ratio elements to be expected. And the final way of working and sizing is to combine the two, as well as use some level of smoothing on the final output. Using this method, you get kind of the best of both worlds, where flat details and curves, they are both well captured, and we also maintain a good quality of the mesh elements thanks to the smoothing between the mesh sizes. All of this, it has to be considered within your context and what type of requirements you have. Because depending on your requirements, you may want to use either a constant global size if the geometry accuracy is not very insensitive, and if the solver is sensitive to small cells. Remember the previous examples about the CFL condition, for example. You may want to use just a geometric size if the physics of the solvers makes it necessary. For example, in external aerodynamics or when computing boundary layer separations, and use the gradation. The last one being use the gradation smoothing with a value that's suitable for your solver, because, for example, finite volume solvers, they are sensible to sharp changes between consecutive mesh elements, and so you may want to use smoothing in order to get proper results. Usually, the meshing technologies, and so our meshing technology, they provide controls over the maximum and minimum cell size that are acceptable. And these are used as a last-minute trim over the cell size. They are global kind of boundaries in our algorithm, because it's done this way in order to make sure the mesh fits the requirements of the solver, because that's the most important criterion. So that's for surface meshing. And before talking a little bit about sizing meshing, how we use volume meshing, I want to talk about some kind of criterions to take into account when you're moving to volume meshing, because the amount of cells that we generate at this step is usually much more important. It can have also a larger impact on the time it takes to compute the simulations. So the goal for volume meshing is to find a compromise between the number of cells as well as the time it takes to run the simulation. We have three recommendations. The first one being that it's best to simplify the model as much as possible, removing small features, holes, etc., as much as possible. For example, here on the motorbike model, we have small details that may not be really relevant to model the structural integrity of the entire structure and its response to fatigue, for example. So you may want to get rid of them. Another example I'm thinking of is when we're modeling, the airflow around a 50-story building, the influence of the chamfers of the windows is negligible on the overall flow of the air, but it requires a high level of details in the mesh, and so you essentially generate a lot of elements for no sensible gain over the simulation results. So that's the first thing to consider. The second thing is to consider reducing the geometry to the most relevant part. So that's when you have symmetries, axis symmetries, or repeating patterns in your geometry. So for example, thinking of tires, for example, you have the same pattern that repeats hundreds, if not thousands of times. And it is interesting to reduce the geometry to only 2 or 3 critical elements that repeats themselves. And you get the same kind of results that you can just repeat all over the tire. And the third one is to consider the locations of the generated volume elements. If you're working on simulating the impact of a mine within a terrain chunk, for example, you may only be interested in generating the mesh elements inside the terrain and not within the corridors of the mine. So usually in our products, we provide options for that. With these recommendations in mind, let's talk about the very basics of how we use sizing and what kind of elements you may use in volume meshing. Okay, so here just for simple volume workflows, sizing is pretty straightforward. We have, again, just like in surface meshing, a smoothing parameter that's used to grow the size within the volume from the surface mesh. And we also recommend to use controls over the maximum and minimum element size that are acceptable in the generated mesh in order to respect the constraints of the solver used. We also recommend to use hybrid meshes that have, for example, a Cartesian core. That's something that we do support, and it may be very useful in order to let to have efficient numerical equation to solve the numerical equations efficiently within the majority of the domain, and then let tetrahedras handle the connection to the surface. So that's for the basics. Okay, and so the light is, sorry, I'm going to wave because the light is turning off. Now that we've covered the basics of surface and volume meshing, I want to give you some examples of more advanced workflows and give you pointers and ideas of things that you can do using our meshing suite. The first example is rather a set of 3 different examples. So it's combining different size constraints in order to create complex kind of mesh generation workflows. The first example on the left here is using different size constraints on the same piece of geometry. Here there are 3 constraints for the single geometry. So a fine size on a given geometry face, a fine size based on the 3D location, and also a constant size for the rest of the geometry. In the middle, you have an example of using anisotropic elements on surfaces. We're able to generate an isotropic element with both our surface mesh technologies and our volume meshing technologies. And these are typically used in order to reduce the overall number of elements while maintaining accuracy to the geometry. The last image on the right is an example of combining kind of multiple sizing constraints, just like the image on the left, but this time for volume meshes. And you can imagine this is useful. This is the image on the right is inspired by, supersonic aerodynamics meshes that you typically need. The second examples of workflow is the use of mesh periodicity. This feature, we call it mesh periodicity, but it's essentially a feature to quote unquote copy and paste a mesh generated on a face to another face or multiple target faces. It's very useful when you have repeating patterns in a geometry to ensure consistency and make sure you observe the same behaviors across the entire geometry. And the other use case for this is you can imagine using it when you have reduced the geometry to its most relevant feature, when there is symmetry, axis symmetry, etc. And you want to reflect the conditions on one face to another face. So that's the example on the right. Another typical workflow we support is the use of boundary layers. So they are very useful in many fields of CAE. The immediate examples that come to mind is, of course, CFD on the slide. I took the example of the cavitation phenomenon that happens on propeller blades. But this feature is also used in other fields such as electromagnetic modeling. These boundary layers, they are made of elements that have to respect hard constraints. And we're able to generate these automatically using simple function calls that specify the type of boundary layers needed, as well as the height of the first layer and other relevant parameters, depending on the height progression for the boundary layers. We are also able to manage the transition towards the isotropic elements automatically, such as you can see on the image with the airplane. So there's no human intervention needed to get a conformal mesh between the layers and the far field. The final example I want to give is the iterative mesh adaptation workflow. On the left, we start from a very coarse volume mesh that has been generating using the default parameters of our volume meshing technology. And then using an iterative process, we build a more refined mesh by specifying local sizes in user-defined areas. Two examples where these would come in handy. The first one is when you're running an iterative solver and after each mesh generation, and you use the results of the solver to refine the mesh in areas where the phenomenon you want to model is the most visible, and coarsen it in areas where there is a lower interest. For example, when you're modeling a crack that propagates throughout the geometry, you can refine where the constraints are the most important and coarsen the mesh in other areas in order to improve the time it takes to run the simulation while also maintaining simulation accuracy. The other use case where it's useful would be to quickly generate complex volume meshes that could take a lot of time to generate in a one-step process. Using this adaptation loop, you would be able to generate a first mesh and then refine it in an interactive manner, which takes less time if you're iteratively changing the mesh than regenerating the mesh every time. So that was all the examples I wanted to showcase. And I think we can move on to the Q&A session.
Yes. Thank you, Arthur. We had a few questions, not too much. So if you feel you have a question you want to raise, don't hesitate. We are here for that. I will let Arthur pick and choose as he's the expert here.
of course. So yeah, we have a couple of questions. The first one is related to what's the gradation. So gradation is essentially a word we use for mesh smoothing. This is the same kind of notion. So it's we use the gradation in both surface and volume meshing as the ratio between consecutive mesh edge length. So if you have an edge of 1 and your gradation is 1.2, then the elements next to it is going to have an edge length of 1.2. Hopefully that makes sense. We have other questions. Let me check. So what type of inputs do you support for surface meshing? Great question. We support essentially, analytical CAD data. So that's going to be anything that is represented by essentially BREP representation. We have tight integration with our own ASYS and CGM modelers, but we also provide an API that is agnostic of any modeler so that it's possible to integrate the meshing technology within any kind of existing application that has a third party or an internal CAD kernel. So other questions?
Yes, just one that I can answer so you can take the time to read.
Sure, thank you.
Can we get the presentation or recording of this webinar? Yes, we will be sending it for you next week. By next week, maybe earlier. And for the rest, would this measure work with an implicit modeler as well? This is a question that I picked for you, Arthur.
Yeah. So currently not. It's not something we do support, implicit modeling. It's not, yeah, unfortunately not. That's I don't really have any better answer to that question. Another question was on the adaptation. How can we make the mesher follow curvatures that don't exist in the initial mesh since we start from a coarse one? So that's a great question. If you want to refine across curvature that do not exist, what we will recommend is used multiple adaptation, consecutive adaptation passes, if that makes sense. So it would be the idea would be to refine, if let's say you have a curve in 3D space where you want to have some points sample there, and you have just only two vertices that are far apart. The idea would be to refine the mesh at these two vertices and in an iterative way, kind of move closer to the curve that you want to approximate. Right now, this is how we would handle such cases.
Mm-hmm. Yeah, we have a lot. Huh?
Okay.
I suggest you check also the open questions.
Yes, I'm looking at.
Because they are both in chat and in question.
Oh, okay, I see. Yeah, I was just looking at the chat here.
Yeah.
So do these two products have hexagon meshing? So I guess you're talking about full hexahedral meshing. So our focus really at the S is going to be there is an emphasis on hybrid meshing where we use a mix of tetrahedral and other complex elements to build a volume mesh, but we do provide full hex mesh technologies that are octree based. Yes, if that is your question. Okay, so a complex question. One of the slowest part of meshing for us involves the non-regularized unite used to generate a conformal mesh of many solid bodies. What advice would you give for that use case? Does support exist, or is it planned for meshing bodies individually and combining the result volume afterwards? Specifically, our models often involve large number of precisely coincident phase. Yeah, that's a real question. That's a great question. We've had kind of an initiative internally to think about all this. We don't really have a great answer for that. The immediate solution I'm thinking of using the technology I'm aware of at Spatial is you would be able to do what essentially you mentioned here, meshing the different bodies individually and then combining them by meshing. Let's say you have two cubes that are next to each other, and for some reason you're not able to perform the non-reg unite between the two. My recommendation, and I've had customers wanting to do that, would be to use the mesh matching feature in order to first mesh the first body in the first place, and then no, sorry, not the mesh matching feature, but we have a way to kind of impose a tessellation on edges, for example. And so you mesh a first body. From this, you get the tessellation of the vertices that are that make where the two bodies touch, essentially. You impose this tessellation on the second body, and then you'd be able to get a conformal mesh between the two. And then you are able to move. Uniting the two meshes is not too hard, and then you'd be able to get through the volume meshing phase using this. So that's my recommendation. So there's that. So what is, okay, so a question more on the offer. What's the relationship between mesh gems and CVM CSM? So mesh gems were the APIs provided by Distine for those who lack context, and DS bought Distine a couple of years ago, who was the provider of the mesh gems technologies. And so essentially, mesh gems is the Distine technology, the CAPIs. CSM CVM is a repackaging of these mesh gems products. And it also includes new technologies that's not within the mesh gems products. But CSM CVM, they are a C++ based APIs with a new and improved architecture and so on. So hopefully that clears the questions. Isn't a mesh faceting decad also an acceptable input for surface meshing? Yeah, that's true. I don't think I answered completely the first question. That was what type of input do you support? I focused too much on CAD input, analytical CAD and BREP, but we support mesh inputs for surface meshing and also hybrid CAD. That's what we call hybrid CAD. So that's BREP data with tessellation in some of the faces or edges. Okay, so I think there are quite a lot of questions. I'm sorry if I can't get through everything. When you have localized mesh sizing, how are these controls based on the patch IDs? Yes, exactly. So it depends on what implementation you're using. I said we have a tight integration with CGM and ASYS and a modular agnostic implementation. So if you're using the modular agnostic implementation, it's in the code, it's up to you to set the IDs. And so you have kind of your map, you know of your mapping already. If you're using CGM or ASYS, then we have functions in the code that takes the face pointer, for example, and you don't have to go fetch the IDs and do some with mapping. There is native support for that. How do you control gradation? Is there a way to control it per input edge basis? What I'm saying is that I want to control the mesh density of a mesh so near an input edge, it is denser, but when it gets farther away, the mesh gets coarser. So you'd be able to control the, so the gradation is right now is a global parameter, but you'd be able to control the tessellation on a given edge. So we have multiple ways of doing that, but you'd be able to control the tessellation on this edge, and using the gradation, the size would get larger and larger the further away you get from the edge. So that's something you'd be able to do. Can you speak? If you mentioned this already, can you speak a bit about performance, multi-threading, multi-core? So it's a challenging question, depending on what we're thinking about. For surface meshing, there are parts of the algorithms that are multi-threaded, but that's not the core of the algorithm. It's mostly optimizations, and the parts that are multi-threaded, they are only able to run multi-thread if the kernel that you're using or the modeler that you're using is thread safe. So for example, that's not the case for us. This is the case for ASIS. ASIS is thread safe. There are implementations of thread safe ASIS, and so we're able to run our surface meshing algorithm in at least leveraging some multi-threading. For the volume meshing technologies, it depends on the feature that's used. There's been kind of an architectural rework. I talked about it. And so there are still things that are waiting to be multi-threaded. The new architecture made it possible to leverage this in the future. But right now it's it's a bit limited. But we have benchmarks that show that we have on average, great. Well, the components that we provide, they generate better meshes, higher quality meshes in kind of the same amount of time, or a lower time than the rest of our internal technologies. So that should be interesting to hear. Can the mesher handle self-intersecting surfaces inputs? What about multi-domain surfaces that share interfaces within tolerance but have different faceting? So the mesher, well, right now, the surface mesher, we recommend to do all the booleans and so on beforehand. You could get away with implementing some sort of because right now the surface mesher, what it does is it creates meshes per body, and it does not compute the kind of the intersections between the two non-conformal faces, for example. So, but however, we have another product that we provide that is able to resolve these intersections. So it's not natively right now in the mesher, but it's also something we are working on with our internal R&D team to kind of bring these kind of capabilities to the product. Okay, so does surface meshing have geometry cleanup function? That's along the line of what I said. We are working on, right now there's nothing native. We have other products that are able to do that, and we are working on capabilities to bring this to the offer.
So I guess we are going to take maybe one more question.
What are some key challenges when performing advanced meshing workflows? So I'm struggling to understand the question here. If we're so yeah, I'm trying to envision what you're asking for. Is it just about the examples that I gave in this presentation, or more complex workflows? If I'm taking the example of boundary layers, for example, usually you have for boundary layers generation, you have already in mind kind of the tolerance, well, the mathematical constraints that you'd have to take into account, because the boundary layer zone is a really well-defined areas near the boundary of between a solid and a fluid. So you have already these things in mind. And the implementation using our tools, it's pretty straightforward. But there may be challenges in some specific scenarios. I know, for example, we manage well external cases, for example, but there are times where we struggle a little bit when generating elements in corners, these sorts of areas, because the approach we are using in order to reliably produce meshes is based on a tetrahedral algorithm. And once this is done, we combine and cut the existing elements to generate the boundary layers, essentially. Using this approach, we're able to generate a mesh in a very reliable way. However, there are times where, because of the unstructured nature of the mesh that has been generated, it's a bit harder to combine everything in a proper way. So yeah, that would be one of the challenge I would see, for example, with boundary layers. But I'm not sure if you had another thing in mind.
All right.
Do you plan on
very much.
just on a final question?
I want the last one. Go ahead.
Do you plan on supporting polyhedral elements? Right now, that's not, I don't think it is on the roadmap. I may come back to you on this with more information, but I don't think it is considered right now. We are very much investing into hybrid technologies right now. Sorry, Ferial, please go ahead.
No problem. I'm just gonna take the hand very quickly to thank you all for your attention today. We were a lot, and we are very happy this topic raised the interest. Just to remind you that we are all across the world, so our technical team and R&D and sales, obviously, and product managers are available to support and answer your question. For the very specific question that couldn't be answered, we will come back to you. And we would like to thank you, Arthur, for this great webinar today. It was a pleasure preparing this with you.
Thank you, everyone, for coming. Thank you, Ferial, and yeah, we will keep in touch. Thank you for coming. Have a great rest of your day.
Thank you very much. Goodbye.